A lighting model is a simplification of the light transport equation, which dictates how light energy distributes, reflects, and transports within a scene. This is a complex equation that can be very expensive to solve computationally. So instead, we often rely on lighting models, which only approximate the light transport equation, but are simpler to calculate and map well to graphics hardware. One such model is the diffuse or Lambertian shading model. It makes the assumption that the surface reflects incoming light equally in all directions. This is a very basic model that works well for non-metallic matte surfaces. This is basically the opposite of a mirror surface. With a theoretical perfect mirror, every incoming light ray is perfectly reflected with the angle of incidence matching the angle of reflection, and zero light is scattered. On the other hand, a perfect Lambertian surface would scatter an incoming light ray equally in all directions. Lambertian surfaces obey Lambert's cosine law, which states that the color of a surface is proportional to the cosine of the angle between the surface normal and the direction to the light source. The surface normal is a unit vector that's perpendicular to the plane of the surface. So this is the vector that starts on the surface and points directly away. Normals are generated by modeling software for us and provided in the mesh object file for each vertex. The dot product of two vectors A and B is equal to the length of A times the length of B times cos theta, where theta is the angle between the two vectors. If both vectors are normalized to be of unit length, then A dot B is equal to cos theta. Therefore, in vector form, the reflected light intensity for any outgoing direction can be calculated using the dot product of the surface normal and a normalized vector pointing to the light source. The intuition behind this equation is that as the angle between the light source direction and surface normal increases, the light is spread out over a larger area. Therefore, the outgoing light at any specific point will be of lower intensity. ScratcherPixel has a very in-depth article going into how the derivation works out to be a cos theta relationship. So if we know the direction to a light source, we can determine the light's intensity at any given vertex on the model by using the normal at that vertex. Okay, let's get to coding. First, let's fix a mistake from last week. In the loadModel function of the model implementation file, my method for setting the default color doesn't actually work. This is because the attrib.colors vector is always initialized to be the same size as the attrib.vertices vector, and filled in with ones wherever a color is not provided in the wavefront file. So this entire block of code can be simplified. I'll remove the current implementation and then simply duplicate the lines above. Change vertex.position to vertex.color, and attrib.vertices to attrib.colors. This will work the same as before, with the default color being white when no color is specified. Okay, now last week we added the normal and UV fields to the vertex struct, but we haven't yet provided these attribute values to a shader. So let's fix that. Just above in the getAttributeDescriptions function, we're going to update this method with attributes for the normals and texture coordinates. First though, I'm going to change how we add the attributes to be more condensed. Update the attributes descriptions to use an empty initialization, and then call attributesDescriptions.pushBack. And in curly braces, we have 0 for the location, 0 for the binding, R32G32B32 as the format, and finally offset of vertex, position. Then duplicate this line and change the location to be location 1 and the offset of vertex to use the color. In my past experience, I've often caused errors due to making a typo when using the previous, more verbose form. But of course, feel free to use whatever you prefer. Then just duplicate this line twice more and update the location value to be 2 and 3. Then change the offset of vertex to use the normal for the third attribute and UV for the fourth. Finally, update the UV attribute descriptions format to only use an R32G32 float, since texture coordinates only have 2 components. Next, we need to update the vertex shader. In the shaders directory, open simpleshader.vert and add 2 more lines declaring the vertex input attributes. These attributes will be at location 2 and 3, so we'll have in vec3 normal followed by in vec2 UV. Next, I would have liked to break up the push constant definition to define the projection, view, and model matrices all individually. This would give us more flexibility within the shader. We could calculate the vertex position in world space by multiplying the model matrix by the vertex position. For some shader calculations, having these intermediate values is necessary, such as when we have a point light in world space, we can use the vertex position in world space to calculate the direction to the point light for each vertex. However, this is where we run into the limitations of push constants, which only guarantee that all platforms support at least 128 bytes. So if we want our code to work on all GPU devices, we can only include at most 2 4x4 matrices in the push constant block. So for today's tutorial, I will instead keep the transform matrix as is, but will remove the color push constant, and then add a second map4 type storing just the model matrix. So the first transform matrix stores the projection times the view times the model matrix, and will be used to transform our vertex positions. Then declare a const vec3 called direction to light, equal to normalize vec3 with values 1, -3, and -1. The normalize function is a built-in GLSL function that converts any vector into an equivalent vector of unit length. Whenever doing lighting calculations, you should always make sure that the input vectors are unit vectors, otherwise you will get incorrect outputs. This technique we are using here is called directional lighting, since every vertex, regardless of what its position is, will use the same direction to the light source. This simulates a light source that is infinitely far away from the object. A real-world example of a directional light source would be the sun, since because it is so far away, light rays that reach the Earth are essentially parallel. The alternative is a point light source, whose position would be much closer to the object being lit. In that case, we would need to calculate the direction to the light on a per vertex basis. We will cover point lights in a future tutorial. The direction to the light is specified in world space. Therefore, to properly compute the lighting, we require the normals to be transformed from model space to world space. We can do this by using the model matrix. The mat3 function converts the 4x4 model matrix to a 3x3 matrix by removing the last row and column. We only need the upper portion of the matrix when transforming normals because they represent directions, not positions, and therefore are not affected by translations. Alternatively, you could also use the full 4x4 matrix and multiply by the normal with an additional fourth component of 0 for the homogeneous coordinate value. But the former method avoids performing unnecessary calculations. So this method of transforming normals by using the model matrix is technically incorrect and only works if certain conditions are satisfied. I will come back to this in just a moment. Finally, we can calculate the light intensity at this vertex value. I will add a float light intensity is equal to the dot product of my normal in world space, comma, the direction to the light. Now, it's possible for the dot product to be negative, which occurs when the normal is facing away from the light source. When the surface isn't facing the light, we'd like the light intensity to have a value of 0. Finally, the output frag color is given by vertex color scaled by the light intensity. For the fragment shader, we can leave it as is, except we need to update the push constant struct definition. So copy these lines, navigate to simpleshader.frag, and overwrite the previous push constant declaration with the updated version. Then navigate to the simple render system implementation and scroll to the top of the file. Let's update the push constant data struct to match the shader definition. Then scroll down to the render game objects function, and inside the for loop, remove the line setting the push.color and declare a new variable with auto model matrix is equal to object.transform.map4. In the line below, remove the map4 function call to use this model matrix local variable instead to avoid performing the calculation twice. And then we have push.modelMatrix is equal to model matrix. We can build and run, and you should see the vase model now shaded with diffuse lighting. Vertices that point towards the light will be lit with a greater intensity, and as the angle between the surface normal and the light direction increases, less light hits the surface and the model will be shaded darker. Surfaces that point away from the light will be completely black. This may appear a little unrealistic. In real life, light bounces all over. It scatters in the atmosphere, it reflects off the walls and objects. Even the darkest part of a shadow doesn't appear completely black to our eyes. And that's because even in complete shadow, some light indirectly reaches that location. It would only be in the deep void of space, where there is nothing for light to bounce off of, would you get a completely black shadow. This type of lighting is known as indirect illumination. Unfortunately, accurately modeling indirect illumination is very, very hard, especially for GPUs. The ambient lighting model is a very simple way to roughly approximate indirect illumination. It assumes that every object receives a small, constant amount of light from all directions, regardless of what direction the surface is facing. Back in the simple shader.vert, I will add a const float value called ambient, and set it to a small value such as 0.02. Then, in the light intensity calculation, I will add this ambient term to the current calculation, so that all vertices receive a minor amount of indirect illumination. Now, if I build and run, the vase model looks a bit more realistic, since even the portions of the model not facing the light still have some amount of lighting applied. Along with the smooth vase object, I also provided a second object file called flatvase that you would have downloaded in the previous tutorial. So if you navigate to your app implementation, we can change to using this object file instead. First, I will adjust my object's translation in the Y direction to move it down by 0.5 to have the model a bit more centered in the view. Then I will instead load models/flatvase.obj. When I build and run, this second vase object has a much more faceted appearance, where each face of the vase is clearly visible. The difference between these model files is based on how the vertex normals were calculated. The smooth vase object uses vertex normals, also known as smooth shading. This is when the normal at each vertex is calculated as if there existed an underlying smooth surface. The flat vase object uses face normals, also known as flat shading. This is when the normal at each vertex uses the same normal as its face. Face normals are more commonly used in low poly art styles, when you want each individual polygon to be clearly visible. Since a vertex can be shared by multiple faces, this means we will have duplicate vertices, one for each face. Because of this, a flat model will have more vertices than its smooth model counterpart. You can choose between flat and smooth shading in Blender before you export your model. If you select your model in object mode, and then open the object drop-down menu, there should be two options, shade smooth and shade flat. Select your desired option, then go to File, Export, Wavefront.obj. Before exporting your model, you will likely want to adjust a few settings. First, under the Transform heading, you should set the transformation to match the coordinate system convention that your engine is using. In our case, that means positive Z for the forward direction and negative Y as the up direction. Next, in the Geometry menu, you will want to select the Triangulate Faces option. You can optionally choose to include materials, but we are not using them currently, and then also have Right Normals and Include UVs selected. You can save this as a preset if you wish to make future exporting quicker. Transforming normals isn't quite as straightforward as simply multiplying by the model matrix as we've done so far. This calculation is actually only correct if uniform scaling is being performed. This means that the X, Y, and Z directions all apply an equal amount of scaling to the object. If you change the scale factor on the vase object to squish the model vertically, and then render it, you can tell this doesn't look quite right. The image looks as if I took the previous vase object and simply squished the image of it. The proper way to transform normals is to use the inverse transpose of the model transformation matrix. If you update the vertex shader to instead use the inverse transpose and re-render, we can see the vase now looks as if it's interacting with the light correctly. I'm not going to prove here why this is true, but I've provided a great resource that goes through the derivation of why normal vectors need to be transformed differently. But now we actually have another problem. Computing the inverse of a matrix per vertex within a shader can be computationally expensive and is typically not recommended. So we have a few viable solutions here. 1. Change your engine to only allow for uniform scaling. So scale becomes a float that acts on the x, y, and z components equally and can just use your model matrix on all your normals. This is actually a very commonly used solution by game engines. Option 2. Compute the inverse transpose on the shader, which is not recommended for performance reasons. And option 3, compute a normal matrix on the host and pass it into the shader. I'm going to use the third method here, even though it has the disadvantage of adding extra complexity to the engine. But if you know that non-uniform scaling is something you simply don't care about, option 1 may be the preferable choice for your engine. Constructing the normal matrix directly is actually not very complicated, so we can avoid most of the computation costs associated with using an inverse function. First, the normal matrix will only be 3 by 3 and can ignore the translation component since only position values are affected by translations. Therefore, the normal matrix is given by the inverse transpose of the rotation matrix times the scale matrix. Using a bit of linear algebra knowledge, we can rearrange this to get the normal matrix is equal to the rotation matrix times the inverse scale matrix. The inverse scale matrix just uses the reciprocal of the scale factors, so we can easily calculate the normal matrix directly. In the vertex shader, comment out these lines and rename the push model matrix to be called normal matrix. Then the normal world space is equal to the normalized result of the push.normal matrix times the vertex normal. Copy the push constant definition and overwrite the push constant struct in the fragment shader so that they match. And then, in the game object header, we will add a new function to calculate the normal matrix. First though, let's actually move the function implementations out of the header to an implementation file. So I will create a new file called lveGameObject.cpp, including the lveGameObject.hpp header file, and then add my namespace. Back in the game object header file, I will copy and remove the mat4 function's body, so that just the mat4 function declaration remains in the header, and then navigate back to the game object implementation. Paste the function body in and add the transform component class name scope before the mat4 function's name. Okay, then back in the game object header, I'll declare a new function that returns a GLM mat3 type called normal matrix. In the implementation file, I will declare the GLM mat3 transform component normal matrix function, and then I'll copy the contents of the mat4 function to use as a starting point. Declare a new local variable of type const glm vec3 called inverse scale and set it equal to 1 over scale. Then in the return statement, change glm mat4 to return a glm mat3 object type instead. And remove the last component from each column vector as well as the entire last column. Then change each occurrence of scale, x, y, or z to instead use the inverse scale local variable. And that's it. The normal matrix is very similar to the model matrix, except it's 3 by 3, ignores the translation component, and scales each column by the reciprocal of the scale components. In the simple render system implementation, we can rename model matrix to instead be normal matrix, and then in the load game objects function, set push.normalMatrix equal to object.transform.normalMatrix. We can't successfully build the project yet because there is a mistake in the vertex shader. The normal matrix is 3 by 3, not 4 by 4. However, In our push constant struct, we will still use a 4x4 matrix because of alignment requirements. I covered alignment requirements in tutorial 9 when I first introduced push constants. A mat3 is actually 3 vec4s, as each vec3 is 3 floats aligned to 16 bytes. So at least the easiest way I know of to pass a 3x3 matrix to a shader with the proper padding is to pass it in as a mat4. And then when you want to use the matrix within the shader, truncate it by using a mat3 conversion. So wrap push.normalMatrix with the mat3 constructor before multiplying it by the normal vector. When we initialize the push.normalMatrix in the simple render system implementation, the GLM library will automatically convert the 3x3 matrix returned by the normal matrix function to a padded 4x4 matrix. So now we can build and run, and you should see the squished vase once more with the correct lighting being applied. You can even render both the smooth and flat vase models at once. All it takes is creating a second game object that uses the other model file. If I do this, shifting the flat vase slightly left and the smooth vase slightly to the right, I can build and run and compare the two vase objects. The vertex positions are all the same and the exact same vertex shader is used by both. The only difference is how the model files specify the vertex normals. I will clean up this unused code in the vertex shader, and that's it for today. Thank you for watching and keep on coding. Cheers.